Okay, hello everyone. Welcome to Advanced Machine Learning and Deep Learning. I hope you're all healthy and safe. My name is Mohammad Burhamayun. So, let's get started. In this class, we will continue, of course, the topic of machine learning, and we will introduce new algorithms, of course, more advanced algorithms and techniques in machine learning and deep learning. We will learn new tools, new techniques, new libraries, and also some of the applications of machine learning in our real life. We will start with more advanced ensemble learning algorithms, and then we will talk about support vector machine algorithms, which are very effective and important algorithms in machine learning. We will cover artificial neural networks that are, of course, maybe the most popular group of machine learning algorithms these days, and then deep learning, as well as some algorithms and techniques for data processing and dimensional reduction and data analytics, such as, for example, principal component analysis for feature selection and dimensional reduction. Similar to 4661, the class will have theoretical and practical aspects of these methods. So we will talk about the theory of every algorithm, and then we will have a Python tutorials to cover programming and implementing that. So again, we use Python, of course, the main programming language for machine learning, and we will learn new libraries this semester, including Keras and TensorFlow for artificial neural networks and deep learning. So today I want to review the main concepts and topics that we need for machine learning. So it will be a review of the main definitions and concepts of machine learning, different types of machine learning, and different terminology in machine learning. And from next week, we will start talking about new algorithms. So we will start with more on ensemble learning. We will learn AdaBoost as an important algorithm in ensemble learning, and then we will continue with other algorithms such as SVM and artificial neural networks. So let's continue. So as I mentioned, today I'm going to review the main concepts and definitions of machine learning that you will definitely need for the rest of this class. You have learned many of them from before, but I feel that we need a review at the first day of class so that everything will be easier for the rest of the semester. So I start with data science. As you know, we talked about it a lot, an interdisciplinary field of research to design and develop automated algorithms to extract knowledge from data, okay, and use for many different purposes. So data science is a very big umbrella. Any tasks that is related to data can be included under the big umbrella of data science, and machine learning and AI and data analytics and data analysis and data visualization, and all of those topics are like subtopics of data science on the big umbrella of data science. Artificial intelligence, or AI, which is a term that we hear a lot these days, is a branch of computer science and data science, because we work with data, because we learn from data, that aims to build machines, and by machines we mean computers, that can mimic human intelligence, such as learning, decision making, and problem solving. So when we talk about artificial intelligence, this is very important that you should notice that it's about intelligence, okay? It's about the brain. So when you see something like this, a robot, for example, is just a physical shell for the AI, okay? So this physical body or physical robot is just a shell for the AI, which is the brain of the system, which is the artificial intelligence part of the system. Let me talk a little bit about the history of AI. So Alan Turing, maybe many of you know this smart mathematician. Back in 1950, he was one of the very first scientists that talked about AI, okay? Maybe the first one. Some people believe he was the first one. So Alan Turing published a paper in 1950, more than 70 years ago, titled Computing, Machinery and Intelligence, okay? And in that paper, in that article, he asked a question. Can machines think? So this was the main question. And he argued that, well, this is a very difficult question to answer. We never know if a computer can think really or not. But an alternative question which is easier to answer is that, can a computer do well in imitation game? And imitation game, probably you know, it's a name of a movie based on the life of Alan Turing. I recommend to watch it. And so this was the question: can a computer do well in an imitation game? And a modified version of this is called Turing Test these days. So Turing Test is a very famous test to recognize if a computer is really intelligent with this definition or not. So this is the Turing test. So in Turing test has three different players. A, which is a human player, a person. B, which is a computer. And C, which is a evaluator, a human person again, who is the evaluator. So person C, the evaluator, he doesn't know if A or B, which one of them is computer and which one of them is human. Okay, so they are in, for example, different rooms. They don't see each other. But C, the evaluator, asks different questions from A and B, written questions. So it writes a question, it sends it to A and receives a written answer. And writes some questions, sends it to B and receives the written answers. But he doesn't know which one is computer, which one is a person. So if the evaluator cannot distinguish the computer from the human after communicating with written questions and answer, the computer is said to have passed the Turing test. Okay? If a computer can pass the test, it could be considered a really intelligent system, very, very intelligent system based on this definition. So it was a computer that was very smart enough so that it can pretend that it is a human. Okay, so it can really pretend that it behaves completely like a human, so that a evaluator with a lot of questions could not recognize that this is a computer. So this is the Turing test, and we had several cases of. So if you're interested in this topic, I would encourage you to search about Turing test and see some of the cases that happened in the history in the past couple of years. For example, computers that could really pass the Turing test, and really the evaluator couldn't recognize that it was a computer. Machine learning is, of course, I would say the most important part of AI and the most important part of data science. So machine learning means learning from data, and we know that, we talked about it before. So all of these things, all of the new AI system, the new data science system, they are all based on learning from data. Okay, so we learn from data. So in this case, for example, when you want to build this computer, the fact is that you need to use a lot of machine learning algorithms to train it. A lot of different machine learning algorithms and technique, and this system learns from data. You don't explicitly program the computer to do this. You just provide the data to the algorithm and it will learn from data. So all of the novel and new AI systems are based on learning from data and learning from experience, which means machine learning. So machine learning is designing and constructing methods that learn from existing data or experience or or past experience and use it for future purposes such as making predictions. Okay, so in fact the machine learning algorithms let a computer learn from existing data or learn from past data and apply its knowledge on future data. Okay, so this is the type of algorithms that we use everywhere these days. Every time you use your mobile, for example, or check your email, you know that we talked about all of these things, many of these things before. Every time you check your mobile, every time you do some online shopping, every time you check your social media like at Facebook and Instagram and different social media, well, they are many different machine learning algorithms that help you with those applications. Okay, and all of those algorithms, again, they learn from data. So self-driving cars, for example, autonomous driving is a popular topic these days. It's a very hot topic, and it is all based on machine learning algorithms that learn from data and experience. So you don't program an autonomous car system to do this and do that. It learns from data. So for example, an expert driver drives with this car for a very long time, for hours and hours and hours, and the machine learning algorithm in this system will learn how to drive from that driver in a training stage. Okay, and well, the companies that are working on these algorithms like Google and Tesla and Apple and so on, of course, they keep training their models. So Google claims that its autonomous driving cars, its system has been trained for millions of hours. Okay, millions of hours of driving in real situations to learn from data and learn from experience. So it's all machine learning. So we learn from data and apply it for future. And we have many different applications for that in our real life. So there are different machine learning algorithms, of course. Last semester in 4661, we learned the fundamentals algorithms such as KNN, decision tree, linear and logistic regression, k-means, which was unsupervised. We talked a lot about gradient descent and random forest. This semester, of course, we learn more about machine learning, more advanced algorithms and techniques, artificial neural networks, deep learning, convolutional neural networks for images and videos, SVM and support vector machine, boosting, bagging algorithms, and PCA, and so on. And I would say after this class, after the series of 4661 and 4662, you can claim that you are an expert. You know most of the topics in machine learning. Okay, so the goal of these classes that I have developed is to make you knowledgeable in this field and make you prepared to get a position, for example, as a machine learning engineer or machine learning expert or data scientist and so on. And as you know, there is another class 5661, which is a graduate level class. It is mostly a research seminar based class that we will even go beyond these topics and will do research and learn more advanced algorithms that high-tech companies uses for different applications these days. All right, so you remember this structure. So this is a very simple the structure of the data and specifically classification. So in this model, as I mentioned here, this is super simple, okay? Super simple. It's a two ideal example. As you see, we have only two features. We suppose that we want to predict cancer, a common important application, and we only have two features: the size of the tumor and softness of the tumor. For example, the information that we can get from a medical imaging method, for example, CT scan or MRI or something like that. And the tumor can be cancerous or benign, and we want to develop a machine learning algorithm to do it for us. And we claim that recently some machine learning algorithms can make better prediction, even better than expert oncologists or pathologists. And this is not surprising. It can happen because an oncologist or pathologist, it learns his information from experience in the past like 10 years or 20 years or 5 years of his practice, and also from medical textbooks that are based on, again, the information of maybe a couple of years before that. But a machine learning can learn from data of many patients, millions of patients from before. Okay, so you can provide more data and more experiences, more historical data to machine learning algorithm. And if you build a advanced enough machine learning model using, for example, artificial neural networks, it will be a better predictor, even better than an oncologist or pathologist. And by the way, it doesn't get tired, it doesn't need salary, it doesn't make mistake because of being tired, it doesn't go to vacations and many different things, okay? But in this case, we have a very simple example, only two features, okay? But usually you may have hundreds of features to make good prediction. And as you see, the data is pretty distinguishable. It's a perfect case that using a simple classifier like a linear classifier like this, you can perfectly classify the data. This is not this is too ideal. To be honest, you don't see something like that in practice, in real life. But this is just to understand the concepts. So these blue ones and red ones are historical data that we have from past. We know what happened to those patients. These are historical data. So for example, we know those patients survived, we know some of them didn't survive, or we did some other tests and examinations. For example, we did biopsy, we took a sample of tumor and really checked it, and we know that this is cancerous or not. Now, based on this data, historical data, this is a new patient that we want to make prediction for. It comes here if we plot it, and from machine learning algorithms can easily predict that, okay, this is a benign tumor. And because we discover a pattern in the historical data, and we see that this new sample belongs to this group. These are the terminologies, the definitions that we talked about a lot, and we will use this in this class. Features, of course, so the size and softness are the features. and training data or historical data that we use to train our model. So these are the labels. And this is, of course, our predictive model, which is a classifier in this case because the data is discrete. And this is your prediction data or testing data. So it can be a data that you use for testing, or it can be a real data that you want to make prediction for. So these are the definitions that we learned in 4661: observations, any data sample, features, labels, training data, again, the data, historical data that you use for training. Testing data is the data that usually we call testing when it is a data that we use for testing your model. But it can also be the actual future data that you want to make prediction for. And training a stage and testing a stage. And training a stage, of course, you know that this is a stage that we provide training data to your machine learning algorithm, and we let it learn from data. Remember that, as I mentioned before, so these are the topics that we talk more about this semester. The model does not have to be perfect, okay? As long as it is close, it's useful. I would say as long as it is better than random guess, that is useful. And remember that your model should tolerate randomness and mistakes, okay? So not all of these data samples are perfect. Of course, we have wrong measurements, we have noise, we have bad data, and your model should be able to tolerate that, okay? It should assume that there are some bad data samples in the data set and can still make a good prediction. We will talk about this later when we talk about SVM especially. We will more talk about this topic. All right, we have supervised learning and unsupervised learning. As you remember, in supervised learning, you provide the data, okay, features, as well as the labels, both of them, to your machine learning algorithm in the training stage, okay? In the training stage, both features and labels will be provided to the machine learning algorithm. It learns, create a predictive model, and you use it in testing stage to make prediction for future data. So in testing stage, we only have features. We provide it to this trained model, and it predicts output for us. Okay? So this is supervised learning. In training, the important part is this. In training stage, labels will be provided to your machine learning algorithm. So later we will see that in unsupervised learning. Again, you have seen that in 4661. In unsupervised learning, there is no label, okay? We just learn from features. We just try to find a pattern in the features. This is an example. Thousands of emails. Contents of those emails will be your feature, will be provided to your machine learning algorithm along with the label, which is a spam or not spam. This way you train a machine learning model that can predict or detect a spam. And when a new email comes, it receives only the features and it detects if this email is a spam or not. And if it is, then it automatically moves it to your spam folder or junk folder. This is what Gmail and all of those email services do. When you receive email, it automatically checks for being a spam or being a dangerous, risky email, and then classify it based on that. Supervised, unsupervised. So supervised is learning from labeled data. Okay, so the training inputs and their known labels will be provided to your machine learning algorithm in training stage. However, in unsupervised, we learn from unlabeled observation. So it's like discovering a hidden pattern in the data. And in some cases, it can be very useful. We don't have anything called label, but still there is a pattern in the data that can help us. So look, this is supervised learning. As you see, the training data, these red and blue samples, are labeled. We know the label of them, and this is the new sample. So if you look at the training data, it has features and it has a label. Both elements will be provided to your machine learning, and this is your classifier. But in unsupervised learning, there is no label. We don't have any red or blue label. Label is meaningless in some cases, but still the data has a pattern, so you see an obvious, so these are features. Still, these are some features. Okay, based on these features, still the data has a pattern, so you know that there are some samples here that are similar, and these samples are probably different from these samples that again look similar. Okay, so we know that there is a pattern in the data, and there are two different types of data samples. These samples, they look like each other, they have some similar features, but we don't know what it is. Okay, when we have a new sample like that, we make prediction and predict that, okay, this new sample belongs to this group, whatever this group is. I don't care, or I don't know, or I don't want to know. I just know that these are some samples that are different from these samples, and this new sample, I predict that this belongs to this group. And in some cases, it can be very helpful. These are some of the applications of unsupervised learning that we talked about last semester. We will learn more this semester. When the label is unknown, okay? In many cases, the label is unknown. For example, in fraud detection, okay? Every time a new fraud happens, and we don't know the pattern of that. Or anomaly detection, okay? Anomaly means an abnormal sample, something which is not normal, something that behaves abnormally, or this is not normal, this is different from normal pattern, okay? But you don't know what it is. In many cases, we don't know what it is, but we just know that this is different from like normal. And there are many useful applications for anomaly detection in, for example, medical cases, in medical applications. So COVID patients, each day we see some new symptoms, and we see some new cases that behaves completely different from before. So that is why we just know that this is not normal, this is different, but we don't know exactly what pattern we should look for. In financial applications like detecting fraud, this is very common because, for example, hackers, every time they come with a new technique, so we cannot label all of those techniques. Maybe a new technique happened, so we just have to detect something which is not normal, a behavior, for example, on an ATM machine which is not normal, or a behavior on online shopping which is suspicious. Okay, we don't know what it is, but we know that this is not normal. So this is the first case that we want to use unsupervised learning. Sometimes we like to do supervised, but we cannot afford labeling the data. Okay, so in image processing, for example, there are millions of pictures of cats and dogs on the internet. We like to have somebody label all of them for us and then use it to train our machine learning model. But we cannot do it. We cannot afford labeling millions of pictures on the internet, but they are there. We still can use them, but in an unsupervised fashion. Don't use label of them, just try to find a pattern in the data. And sometimes we don't care about the label. I talked about this before, like clustering in marketing. There is no label. We just want to cluster this product into like 3 different groups, for example, or 5 different groups, for example, small, medium, or large, XL, and XXL, something like that. Sometimes applying an unsupervised learning ahead of a supervised learning can be useful, and I talked about this before. And okay, and sometimes we want to manipulate the data without considering the label, like dimensional reduction, specifically PCA, principal component analysis, that I will cover this semester. So this is a picture that I really like. It tells us what unsupervised machine learning can be used for. There is a pattern here, right? Sometimes we don't know what it is because we don't look for any specific pattern. We don't train our machine learning model to search for a tiger because we don't know if it's going to be a tiger or lion or a snake or bird or whatever. We just search for anything which has a different pattern compared to the rest of the image. And this is something here which has a different pattern compared to the rest of the picture. Okay, that's why we can find this pattern using like unsupervised learning.